In our next lesson, in our chapter of the electronic structure of atoms, we examine the quantized energy and photons. The wave model of light explains many aspects of its behavior. There are several phenomena that this model just doesn't explain well. Three of these are particularly pertinent to our understanding of how this electromagnetic radiation and atoms interact. The first of the three, the emission of light from hot objects, which is referred to as blackbody radiation simply because the objects being studied appear black before heating them. The second of our three phenomenon, the emission of electrons from metal surfaces on which light shines. This is known as the photoelectric effect, which Albert Einstein won his Nobel Prize for. And the final phenomenon, the emission of light from electronically excited gas atoms, known as emission spectra. Emission spectroscopy, sometimes you'll hear it called. In this lesson, we examine the first of the two and leave the third phenomenon for the next lesson. You know that emission spectra, we've had a background in our first year chemistry when we examined the lab flame testing, exciting electrons to see what type of wavelength is emitted as they go from the excited state back to their ground state. Let's examine hot objects in blackbody radiation first. When solids are heated, we know they emit radiation as seen in the red glow of an electric stove burner or the bright white light of tungsten light bulbs. The wavelength distribution of the radiation depends upon the temperature. A red hot object being cooler than a white hot object. In the late 1800s, a number of physicists were studying this phenomenon, trying to understand this relationship between the temperature and the intensity and wavelengths of that emitted radiation. The laws of physics at the time just were not accounting for these observations. So in 1900, we had a German physicist named Max Planck, Planck. Planck is somehow, I think we've Americanized the Planck, so you'll hear it either way. He solved a problem making one daring assumption. He assumed that energy can either be released or absorbed by atoms, but only in discrete chunks of some minimum amount of energy he termed a quantum. The quantum means a fixed amount. When he studied fixed amounts of energy, he realized that he was beginning to lay the foundation of a whole new mathematics called quantum mechanics. He proposed that the energy, represented with the symbol E, of a single quantum would equal a constant times the frequency of this radiation. So again, much of the mathematics applied by Max Planck determined this very simple yet eloquent equation. E is equal to h nu, where E stands for energy measured in joules. Here we have a simple mathematical formula, E equal h nu. E stands for energy. We know energy is measured in joules. H is a constant. It's known as Planck's constant, Planck's constant. And nu, of course, is the frequency of which the radiation is being emitted. If you see the expression delta E equal nh nu, n stands for an integer, 1, 2, 3, a whole number. Where there is only discrete chunks of energy, it will never come out to be half a step or a 3/4 of a step, but always a full step of energy being released. A model for quantized energy could simply be comparing a ramp to a staircase. They both lead to the same place. However, there's an infinite amount of change when I have a ramp, but I have a very discrete amount of change. I can't place my foot halfway up the step and step up. I must go 1 step, 2 step, 3 steps, where the number of steps is a whole number of integer. The same is the idea of quantized energy. Energy comes in packets. Quanta is the minimum amount of energy that drive these packets of energy. How much will be released? Is it 1 step worth, or 2 steps, or 3 steps, 1 joule, 2 joules, or so forth? N is always a whole number integer. H is called Planck's constant and has a value of 6.626 times 10 to the negative 34 joules times seconds. Now I use 6.63 times 10 to the negative 34 joules times seconds. I carry 2 decimals instead of 3 from mathematics. According to Planck's theory, matter is allowed to emit and absorb energy only in these whole number multiples of h times nu, such as 1, 2, 3, and so forth. If the quantity of energy emitted by an atom has an integer of 3, for example, we say that 3 quanta of energy have been emitted. Quanta, of course, is the plural of quantum. Because this energy can be released only in specific amounts, we say that energy is quantized. Their value is restricted to certain quantities, a whole number. This revolutionary proposal that energy is quantized was proved correct, and Max Planck was awarded the 1918 Nobel Prize in Physics for his work in the quantum theory. If the notion of quantized energy seems strange, it might be helpful to just draw that quick analogy of comparing a ramp to a staircase. As you walk in a uniform continuous matter, your potential energy up a ramp increases with an infinite amount. When you climb a staircase, you can only step on individual steps and not between them, so that your potential energy is restricted to certain whole number values. It is quantized. If Max Planck's quantum theory is correct, why aren't its effects more obvious in our daily lives? Why do energy changes seem continuous rather than quantized or jagged? Well, notice that this energy, h times nu, is extremely small. So Planck's rules regarding the gain or loss of energies are always the same, but we're looking at objects that are in an infinite microscopic world, not the macroscopic objects that we observe every day. We cannot notice a quantum of energy in a macroscopic world. It's just completely unnoticed. But when you're dealing with matter at the atomic level, the impact of quantized energy is far more significant. So here we have a formula, let's make this. I'm going to add a slide. And maybe you want to do this on a separate sheet of paper. I'm going to just keep tabulating through our chapter important equations and important constants, just to have in one place as we gain knowledge through our lessons. The first came from lesson 1, where the speed of light is equal to the wavelength times the frequency, c equal lambda nu. The constant here, 3.0 times 10 to the 8th meters per second. We know that wavelength must be reported in a meter and frequency must come to us in a per second just to make the units work. We've just been given a new formula in lesson number 2. The quantized amount of energy is equal to Planck's constant times the frequency. Now h is a constant. I use 6.63 times 10 to the negative 34th power joules times seconds. H is a constant. Remember, nu is the frequency, must be in a per second. Speed of light is equal to wavelength times frequency. Wavelength is in a meter. Frequency is in a per second. Speed of light, meter per second. Energy comes to us in a unit called joules. If the number is very large, sometimes we hear kilojoules. Joules of energy is equal to Planck's constant, which is joules times second, times the frequency, which of course comes in a per second, second raised to the negative 1 power. These are the two equations that will carry us through lesson number 2 quite nicely. We talked about blackbody radiation and the way that Max Planck studied that to come up with the idea that energy is quantized. The second phenomenon that the simple wavelength of light does not explain is called the photoelectric effect, Albert Einstein's contribution to the quantum mechanical model. A few years after Max Planck presented his theory, scientists began to see its application to many great experimental observations. It just soon became apparent that Planck's theory had within it seeds of a revolution in the way that the physical world is going to be viewed. Albert Einstein in 1905 used Planck's quantum theory to explain what is called the photoelectric effect. His experiment showed that when you shine a light on a clean metal surface, that electrons are ejected or emitted. They bounce out. For each metal he was experimenting with, there appeared to be a minimum frequency of light below which no electron was emitted. So we had to reach this minimum threshold for the photoelectric effect to work, the ejection of electrons to complete a circuit. When you walk into the doors at Myers and they open automatically, you're completing a circuit when you break that light. Photoelectric effect, for example. To explain this photoelectric effect, Einstein assumed that the radiant energy striking the metal surface is behaving like a wave, but rather it's a stream of tiny energy packets. These packets he called photons. Now, a photon is an energy packet of light. It behaves as a tiny particle. So here is the first time we introduce this duality of light. The duality that light acts not only as a wave of energy, but a packet of matter. Extending Planck's quantum theory, Einstein deduced that each photon must have an energy equal to Planck's constant times the frequency of light. So again, E equal h times nu. Energy of a photon that's striking a metal surface is equal to Planck's constant times its frequency. You remember Einstein's famous experiment, E equal mc squared. E is the energy, m is mass, and c is the speed of light squared. So he was able to manipulate his known equation with Planck's equation and was able to deduce by calculating the mass of a photon. The mass of a single photon can be calculated by using Planck's constant set over the product of wavelength times the speed of light. Let's put into practice what we know. We want to calculate the energy of a photon, one photon of yellow light whose wavelength is 589 nanometers. Now remember the two equations that we know? The speed of light is equal to the wavelength times its frequency. The energy is equal to Planck's constant times the frequency. So see, the ultimate variable we're being asked to solve for here is joules of energy. And in order to calculate joules of energy, we need the frequency. The story problem here gave us the wavelength. So in our first step of our problem solving, we'll turn the wavelength into frequency and then use that frequency to pull out energy. We know the speed of light is a constant, 3 times 10 to the 8th power meters per second. The wavelength provided for us in our problem was 589 nanometers. I convert that to the meter so the units make sense in the algebra problem. Let's pull out the frequency in a per second. Pulling out frequency has us calculating the speed of light, 3e8. And I'm going to divide by 589, e negative 9. And the frequency of our photon is 5.093, let's carry 2 decimals, 5.09 times 10 to the 14th power hertz or per second. Now that we have the correct unit in a per second, we can calculate the energy using Planck's formula, E equal h nu. The energy of our single photon of yellow light is equal to Planck's constant, 6.63, times 10 to the negative 34 joules times second. I'll multiply that by 5.09 times 10 to the 14th per second. Notice how seconds will cancel and you're left with joules of energy. So while I still have that on my calculator from taking speed of light divided by wavelength, I'll multiply that by Planck's constant, 6.63, e negative 34, and I find an answer, 3.376, let's use 2 decimals, 3.38 times 10 to the negative 19th joules of energy. In our two-step process, step 1 converted wavelength to the frequency. We needed frequency to plug into the equation to solve for energy. Straightforward algebra. Let's try a next sample exercise. A laser light emits a light with a frequency of 4.69 times 10 to the 14th per second. What is the energy of a photon of the radiation from this laser? Well, here we're given the frequency directly, and I know to calculate the energy, I'll just simply use Planck's constant times the frequency. I do not need to convert a wavelength to frequency because it was provided already. Planck's constant is not 3. There we go. 6.63 times 10 to the negative 34th joules times second times that provided frequency, 4.69 times 10 to the 14th per second. And we'll end up by canceling units with joules of energy. Hit with me, Planck's constant, 6.63 e negative 34. Multiply by 4.69 e 14. And the energy comes to us 3.11 times 10 to the negative 19th joules of energy. This next sample exercise goes hand in hand, so I should have labeled these like part A, part B, part C. So we'll need this answer to go on to the next part. So let's just take a real strong note here, because I have to change slide. 3.11 times 10 to the negative 19 joules per energy for a single photon. That's the key here. This is how much energy is released for one photon. This will end up being my conversion factor. So let's say that this particular problem was part A. This particular problem will be part B. And underneath that, the next part here will be part C. So they'll go right in order. Part A, part B, part C. From our part A, we had 3.11 joules of energy being released. Whoops, I forgot my times 10. 3.11 times 10 to the negative 19th joules of energy released for a photon. So this is now going to serve as our conversion. So what if we had a laser emitting a pulse of energy where 5 times 10 to the 17th photons were being released? What's the total energy of that pulse? So if I had 5.0 times 10 to the 17th photons being emitted, my conversion factor from the solution of part A says, you know what? There's 3.11 times 10 to the negative 19th joules of energy released for every photon that is emitted. See what's happened? We can cancel the unit of photon and go right directly to the joules. So that's what we'll do. We'll use our conversion from part A. If 5e17 photons times 3.11 e negative 19 set over 1, canceling the photons, and what we find is 0.1555, I'll say 0.16 joules of energy. If one photon required this amount of joules, this many photons would require 0.16 joules. So this little ratio. And now in part C, if the same laser emitted 1.3 times 10 to the negative 2 joules of energy in a single pulse, how many photons would be emitted? Remember that conversion factor. Now here, given joules, we need joules to cancel, and we want to go to photons. Previous example, letter B, we wanted photons to cancel and go to joules. So I have to just flip this around to get my units to cancel. In every one photon, 3.11 times 10 raised to the negative 19th joules of energy. Let me be sure that's the correct conversion. Yep. 3.11 times 10 to the negative 19th joules for every one photon. Writing our conversion this way cancels joules and brings us into the unit of photon. So here I'll take 1.3 e negative 2 divide by 3.11 e negative 19. Did you get the same as me? Make sure. 4.18 times 10 raised to the 16th power, and that's a number of energy packets of light referred to as photons. So what is it? This is duality of light. In our lesson number 1, we studied light as a function of a wave. Is it a wave? Yes. Is it a particle? Yes. Yes to both questions. We call it the wave-particle duality. Between Max Planck and Albert Einstein, performing all kinds of wonderful mathematical and experimental proofs, we now know that the particle of light and a wave of light is now going to be used to describe the electron as it moves around its nucleus. Electrons, both as a particle with a mass and behaving as a wave, like a light particle of energy. Let's keep practicing. If you take a look at your additional exercises, this will be on the top of page 4 in our note packs. And I'll just come up with, does this match? Yeah, here we go. Calculate the smallest increments. Let me give myself some room and we'll just work these together. The additional examples. The first reads, calculate the smallest increment of energy that can be emitted or absorbed at a wavelength of 438 nanometers. Well, keep in mind what we want to know. We want to know energy. To know energy, we need Planck's constant and the frequency of our light. However, this problem gave us wavelength. So we'll need to do a quick conversion using the speed of light to convert our wavelength to frequency. We know the speed of light is a constant, 3.0 times 10 to the 8th meters per second. The wavelength given to us was 438 nanometers. Notice how I write nanometers, just 10 to the negative 9th meter. Let's pull out the frequency of our radiation. So speed of light, 3e8, divide out your wavelength of 438 e negative 9, and our frequency of our light, 6.85 times 10 to the 14th per seconds. Now I can solve for the energy. I have that required variable of frequency by using my speed of light conversion. I can solve for energy by using Planck's constant, 6.63 times 10 to the negative 34th power, include the unit with me, a joule times second. So that way I see when I multiply by my calculated frequency, the second unit cancels, and I'm left with joules of energy. I'll just leave my calculator screen as it was from the previous solution. Take that answer and multiply by Planck's constant, 6.63 e negative 34. And I find joules of energy. Do you find the same? Oops, I need a marker. How about 4.54 times 10 to the negative 19th power joules of energy? Calculate the energy of a photon with a frequency of 6.75 times 10 raised to the 12th power per seconds. Well, this is nice. Frequency is given to us. It's pretty straightforward. We know that the energy can be calculated by taking frequency times Planck's constant. We're working to memorize Planck's constant, 6.63 times 10 to the negative 34th joules times second, times that given frequency of 6.75 times 10 to the 12th power per second. How many joules of energy do we have? Hit it with me. 6.63 e negative 34 is our Planck's constant value, times 6.75 e to the 12th power and I find an answer. I hope it matches. 4.475. Let's do 4.48 times 10 to the negative 21 joules of energy. Let's read our next problem. What wavelength of radiation has photons with a provided energy of 2.87 times 10 to the negative 18th joules? And in what portion of our electromagnetic spectrum would this radiation be found? So we'll have to go back and look at our notepad to find where the wavelength ends up on the electromagnetic spectrum provided for us earlier in the notes. Or in your textbook, we can take a peek there. Well, let's do this problem. So the first thing we need to do is pull out the frequency. From the frequency, we can easily convert to find the wavelength. So remember, this is our target. What is the wavelength? So we're going to need a two-step process. We'll use the energy, divide out Planck's constant to find the frequency. And from the frequency, we can convert that into the wavelength. So the energy given to us in our story problem, 2.87 times 10 to the negative 18th joules of energy, set equal to Planck's constant, 6.63 times 10 to the negative 34th joules times second. And here's the frequency. The unit will come out in a per second. So take our energy, 2.87 e negative 18, divide out Planck's constant, 6.63 e negative 34. Frequency here comes out as 4.328. So how about 4.33 times 10 to the positive 15th power per seconds. Now let's convert that into its wavelength. 3.0 times 10 to the 8th meters per second. Solving for wavelength. And 4.33 times 10 to the 15th power per seconds is our frequency. Distance will come out in a meter. So 3e8, our speed of light constant, divided by that previous answer, and I find 6.93 times 10 to the negative 8th meter. You might see that written, if I want to slide the decimal one more, 69.3 nanometers, either way. But what I'm doing that for is to try to figure out where are we on our electromagnetic spectrum. So keep in mind where I'm referring to. This was in a previous lesson when we first introduced the concept of the electromagnetic spectrum. We had the different wavelengths given to us here. So we're looking at a wavelength quite short, nanometer, not even in the visible spectrum. So right in this range is a nanometer. Right here probably we're greater than 10. Looks like UV radiation. So our calculated answer of 6.93 times 10 to the negative 8th, we called that 69 nanometers. 69 lies between 10 and 400. So you're in the UV range, aren't we? So that's as simple as that could be, is just finding where that magnitude of the number lies in our answer. Oh, I'm trying to find that slide. Here it is. So looking at the magnitude of the wavelength, this looks to be in the UV range, ultraviolet range. Another example, the element molybdenum. Molybdenum metal absorbs radiation with a minimum frequency of 1.09 times 10 to the 15th power per seconds before it can emit an electron from its surface via the photoelectric effect. What's the minimum energy needed to produce this effect? We're going to be looking for E. What wavelength will that be? So converting frequency to wavelength, and using that then as a conversion to find 120 nanometer wavelength to find the energy. So again, we have a part A, a part B, a part C, and yet it's still the same two calculated relationships, C equal lambda nu and E equal h nu. The tie between the two formulas is the frequency. So let's start with that first part. What is the minimum amount of energy needed to produce this effect? So there's, we're solving for energy. E equal Planck's constant, 6.63 times 10 to the negative 34th joule times second. And that frequency that was given to us, 1.09 times 10 to the 15th power hertz or per second. Let's take Planck's constant and multiply by the frequency. Are you hitting with me on your calculator? 6.63 E negative 34 times 1.09 E 15. And I'm finding the energy as 7.2, and I'll round 7.23 times 10 to the negative 19th joules of energy. What wavelength will provide a photon of this energy? Well, that's just converting this frequency into a wavelength by our familiar C equal lambda nu. So the speed of light, constant, working to memorize. We want to convert frequency into a wavelength, so we simply divide. Alrighty, let's see what we find. Whoops, I didn't want to do that. Wavelength will come out in a meter. So 3E8 divided by 1.09 E15, and I get an answer that says 2.75 times 10 to the negative 7th meters. You might see that reported as 275 nanometers. If molybdenum is irradiated with light of a wavelength of 120 nanometers, what is the maximum possible kinetic energy of the emitted electrons? Well, so here's all we're saying is, here is the maximum, we're trying to find the minimum. So let's begin. For part C, we have 120 nanometers. So let's convert that into a frequency. We're looking for energy, so we're just using our two algebraic expressions to turn our 120 nanometers to find its frequency. So a simple conversion using the speed of light. Oh shoot, I forgot my unit there. Meter per second. So 3E8, divide out your 120, E negative 9. insert divided by. All right, I think I hit that correctly. I found 2.5 times 10 to the 15th power, and that is the frequency, so it's a per second. We want to know the maximum kinetic energy. Energy is measured in joules, so we'll simply take Planck's constant, 6.63 times 10 to the negative 34th, joule times second. Use that calculated 2.5, I should include 2 decimals there, times 10 to the 15th power as our calculated frequency. We'll find the kinetic energy. Times 6.63, E negative 34. So 2.5 E15 times Planck's constant. Hit enter and I'm finding 1.66 times 10 to the negative 18th joules of energy. In our lesson, we've calculated energy, quantized amounts of energy coming to us in joules. Energy can be calculated by knowing Planck's constant and the frequency, and easily converted, if I'm provided a wavelength, easily convert into a frequency by knowing the speed of light constant. So to highlight the lesson, the duality of light, this really important concept, because it's now going to be applied to an electron in the next lesson. Light not only is a particle, it is a wave. And we've just calculated wavelengths and frequency as a wave nature of light. And using joules of energy, we treated it as a packet of quantized amount of matter, called a quantum. You're ready for lesson number 2's assignment and the quiz. Keep practicing in the assignment, and then when ready, take your multiple choice quiz.